not inform you in advance that I could not come, and I think uh, most of you expect I come and join the lecture, but I'm so sorry about it. Um, so let's start our lecture. Today we will start our first uh, lecture about characterization of nanoparticles. Basically, characterization of nanoparticles are very important and very important issue because whatever you synthesize with whatever technique you use, solution based or uh, dry based or um, up to down or down to top approach, you need to characterize your material. And without characterization, you don't know what is synthesized and what is the characteristic. So the importance of characterization is a lot. For most of studies which publish in material and nanotechnology, the characterization is the core of a study. So after synthesis or fabrication of nanomaterial or nanoparticles, you need to characterize it. And the characterization can be done with various techniques. I categorize them with photon based techniques, electron based techniques, and probe techniques, scanning probe techniques. So basically, what we mean by characterization in these techniques is that we try to use a material or a particle which interact with our nanomaterial, and based on that interaction, we can synthesize some data about our material. And whatever is the properties of our material, whatever is our uh, characteristic of our material, we can publish that data and we can find an application based on characteristic. So, as you know, nanomaterials have different characteristics than the bulk material, larger scale material. And when we talk about the characteristic of our material, we should know that what we are talking about. It is very important what we are talking about. We are talking about the nano characteristic. We are if someone talk about, for example, silver. Silver. What is the characteristic of silver? The characteristic of the silver is different based on its scale. When you reduce down the size of the silver particles, the characteristic start to change. So the nano characteristic of silver is different, much different than the macro characteristic of silver, and also bulk characteristic of silver or gold also, or any other material. So these characteristics are core of application. When you find a new characteristic on a new material or a synthesized nanomaterial, you start to look for application because usually these characteristics are unique. They are very advanced. They are these characteristics are something which people are not uh, aware of it 100 years ago or 50 years ago. These are advanced characteristic of your material or advanced properties of your material. To characterize your material, you use, as I told you, a particle or a material or light or something which interact with your material. You need to interact something with your material. Basically, we can use photons as that characterizing tool. Sorry. This characterizing tool can be an object, can be photon, can be a probe, can be a needle, can be electrons. So today we are going to discuss the characterization of material with photons. Okay, nanomaterials with photons. Basically, when you shine a material, a crystalline, or a network of a lattice of material with short wavelengths, X-ray, something happened which is called Bragg diffraction. Who knows what is the Bragg diffraction? Anyone here is familiar with the Bragg diffraction? Please let me know. Anyone here who read or hear or studied Bragg diffraction before? Anyone? Any student knows Bragg
سلام
diffraction?
دكتور.
Salam. Do you know Rasul? Who do you know, Russell? Do you know
ب...
what is the
زب...
Bragg diffraction?
ببخشید دکتور. بله
Mm,
به حال فیزیک حال جامد گرفتم.
So can you please talk about Bragg diffraction in Arabic to your friends
ب...
and your
براكس.
yes about the Bragg diffraction. What is the Bragg diffraction?
أر...
Yes, in Arabic, please. Russell? Yes, yes,
لو براك أرق
yes,
أن
yes,
معامل الوسط لامدا ويف لينث الطول الموجي ايكوال يساوي 2 دي المسافة فاصلة يعني بزبان فارسي
yes,
ساين الثيتا. هذا دكتور.
yes. So when you're a photon or a wave interact with lattice or an order lattice or order lines of particles or atoms, basically they will diffract in space. In some angles, you will see the reflection of your reflection back of your X-ray, and in many angles you don't see anything. So first time Bragg's basically you all of you saw Bragg diffraction when you see some oil or some petrol droplets or gasoline on droplet gasoline droplets thinner than 1 micron on the water, you will see different color of light. You will see different color of light. You see red, you see blue, you see green in different angles. So that's what we all of you saw in um, winter in the petrol station. Okay. Uh, called petrol thin film interference. Sometimes, most of the times, you see it in the winter time when there is some basically droplet of petroleum on water, on a thin layer of water. So in some angles, you see different colors. Okay, this is quite well known in the basic physics, in the optics, and people study that for many years for studying thin films, and they found that everywhere you have a thin film of oil or petroleum, and you shine it with different angles, the light will scatter with different angles. So you will have a colorful pattern, and with the based on the angle, okay, which you see the color of light, you can see different wavelengths of light and different thin film, different thickness of thin film with different angles. If you move your head, you see the colors is changing. The reason is that the thickness and the angle that the color are reflected back to your eyes is different based on the wavelengths of light. So, if according to the Bragg diffraction equilibrium, when you have shorter wavelengths, they will diffract on the shorter angles, and when you have higher wavelengths, they will diffract on the higher angles, basically. So this can be used for measuring the thickness of oil or a thin film on water. Okay, because the thickness is around the wavelengths of the light. The visible light is diffract between the wavelengths of the visible light is different. Do you know what is the visible light wavelengths of the visible light? Do you know that? Anyone knows that? Why you don't? Hmm? The visible part of the light is the part which the photons have the wavelengths between 400 nanometer to 700 nanometer. Okay, so between 400 to 700 nanometer is the wavelengths of the visible light. So the diffraction happened only when your light wavelengths is around the thickness of the thin film. So if the thickness of the thin film is around this 400 nanometer to 700 nanometer, you will have the diffraction of light in that area. But if we are talking about the if we are talking about the diffraction of light in the tiny layers of atoms, uh, can it be happened? The question is that can the light diffract? Light can diffract between the thin films of oil. Okay, so if you have a thin film of oil, it can diffract or it can interfere different angles of light. Okay, but the question is that can light diffract between the atomic layers? Anyone have any idea? Can light diffract also between atomic layers of material? A thin film of material can interfere or reflect or diffract light. Okay, a thin film. The thin film can be a very thin layer of oil. The answer is that yes, it can. But in order to have diffraction or interference between reflections of light from atomic layers, your wavelengths should be around the wavelengths of around the distance of your atomic layers. So the wavelengths you use, lambda, should be in order or around the distance between the atomic planes or atomic layers. So what is the size of an atom? What is the order of size of an atom? Who knows that? Who knows that the size of atoms? The order of the size of atoms? It's nanometer, or it's micrometer, is a millimeter, or it's a meter. What is the size level of an atom? Hey, physicists, you are physicists. You don't know what is the size order of an atom? Size order of atom or order of size of atoms are in the level of size level of atom are in the level of angstrom. So around 145 angstrom. Okay. So if you have a two atomic layer, you need the angstrom level to have diffraction of light. So the light which has these wavelengths is 10 to minus 10 is basically considered as a X-ray. And angstrom is 110 to minus 1 meter. Okay, so if you want to have the diffraction or interference of light between the atomic layers, you need X-ray, not the photon, not the large wavelengths. You need only X-rays. You can do it with X-ray. So basically, usually we use the 1.5 angstrom wavelengths of uh, photons, which called CUK alpha. We use that beam, X-ray beam, for characterize the material with X-ray. And when you shine the material with the beam of X-ray, at you shine a material with the angle of theta, and the material only reflect back the X-ray at the angle of theta again, if the Bragg law or equation is valid. Means the n lambda equals the 2d sine theta. So if this equation valid or works, then the light will reflect back between the atomic layers. The photons of X-ray will reflect back. But if this equation, the Bragg law, is not valid, the light won't reflect back at the angle of theta. The light will goes through or disperse in the space. So if you want to have the diffraction, you need to have a tool which called X-ray diffraction tool. Basically, X-ray diffraction tool consider of a X-ray lamp. Usually, it's a cathodic lamp with the uh, with the copper anode. Okay, the electrons will the lamp is in the high vacuum, But when you put it on the high tension, very high tension, some kilovolts, the electrons will eject from the cathode and will shine the anode. Okay, the electron will shine the anode, and when the electron will shine the anode, it will give you X-ray because of the uh, atomic level of the copper. It excites copper. Yeah, your electron will excite copper, and copper start to shine a wavelength which is equal to 1.5 angstrom. Then that wavelength can be used later for characterization of your material. When you shine your material with that X-ray beam, the electrons will travel, the photons will travel through your structure of your material, and they will reflect back only when this equation n lambda equals to 2d sine theta is valid. So based on the atomic layers distance, you will have different reflection or different uh, reflection angles from your material, and you will have a plot, a pattern, which is called XRD pattern, X-ray diffraction pattern. So X-ray diffraction pattern simply is a pattern of your intensity of your reflected beam versus the intensity versus the angle which you you shoot your material with that. So with this simple equation, we can measure many characteristics of your material. You can measure the crystal distance or lattice distance of your material, okay, between your planes or between your crystal planes. You can measure the uh, you can estimate the size of your crystal based on the Weisharer equation and many other parameters. Uh, just a minute, I will be back in a minute. Uh, as I told you, can you hear me?
Yes, doctor, yes.
Yes, doctor.
Yeah. Sorry, I changed my place. So actually, I changed my room. So that's why it takes a time. So the basic information we can receive from the X-ray diffraction is the distance between the atomic uh, layers or D, and other information. Uh, you can, if you know the angle which your material reflect back uh, the X-ray, you can simply measure the distance between your atomic layers. But the question is that, so you can do it for any crystalline material, any crystalline material, iron, sugar, diamond, whatever is which is crystalline. You can do this experiment and measure the uh, distance between the atomic layers. But the interesting question is that, can we get more information from this experiment? Yes, we can. And other question is that, does crystal size or particle size change the distance between the atomic structure or between the atomic layers of your material? What do you think about that? Can the crystal size or particle size affect the distance between the uh, atomic layers? What you think about that? So if you we have nanomaterial, does its crystal size affect its atomic structure or crystal structure? Again, the answer is yes. So let's see what will happen. Imagine these atomic layers or crystal layers or crystal planes, which reflect back the X-ray photons, are mirrors. All of you have mirror in your homes. Imagine it is a mirror. So when you have a large crystal, your mirrors are quite large. And when you have the small crystals, your mirror will be quite small. So what is, I have a question. Reflection of the light or photons is better from the mirrors, small mirrors or large mirror? Which one is better for reflecting light? A small mirror or large mirrors? Large mirror reflect light better or a small mirror? Do you know mirror? Do you have any idea?
Yes, Victor. I think is a large mirror
Exactly,
is better.
exactly. So if you have the larger mirror, it's reflect back more photons. Exactly. What is your name, sir? Who was
Uh, I'm Ali Karim.
Ali Karim? Thanks, Ali.
Thank
So
you very much.
basically, no problem. Basically, when you have the larger crystals, your crystal planes or atomic layers which reflect back the X-ray is larger. So they they reflect the light much better than the smaller crystal. Okay? So when you increase the size of your crystal, your reflection is much better than the small crystal. In other words, when you use nanomaterial or a small crystals of materials, your reflection is not very good. So when your reflection is not very good, the reflection, the diffraction pattern based on the diffraction angles is wide. The peaks are lower when you have the nanomaterial. And when you have the large crystals of your material, the diffraction is quite sharp. The intensity of your diffracted beam is quite high. So the first person who studied this phenomenon called Scherer, Debye and Scherer, were two scientists who synthesized this equation. The D equals to K lambda over beta cosine of theta. What is beta? Beta is the wave, is the half, if you have a peak like this, what is the intensity of this? The peak is from here to bottom of the peak, okay? We come to the half of the peak here, and the width of the half peak maximum is called beta. So the D is size of your crystal, and theta is the angle which diffraction is happening. Okay, it's called half v the this beta called width half maximum. So if you have the half of a peak, which is what the widthness of the peak, half of it is at here, and the width of the peak at the half is called beta. So you can estimate the crystal size of your material with this equation. Who is coming to the class? Please, all the students present in the class. I get many people who come to the class when I'm giving lecture. So when I'm giving lecture, students have to listen. They should not go out and come in. Please stay in the class. Don't go out and come in. Okay?
Sorry, Doctor, because the internet in Iraq is not good because
I see.
is the classes.
I see. So with this simple equation, we can estimate the size of our crystal. But and if I gave you some X-ray diffraction peak, one in top and one in bottom, and ask you which of this material, the material on top or the material on bottom, which of them is nanocrystalline? What is your answer? This is nanocrystalline, or this is nanocrystalline? What is your answer? Top or bottom? And why? This is an example of questions come in the exam. I show you two diffraction pattern, X-ray diffraction pattern, and ask you which of them is related, corresponding to a nanocrystalline material and why. Any idea? The material on top, yes. Any idea?
Yes. I think is down Christian because different between wave length. I think that.
Yeah, that's right. The material on top is the micromaterial or is a powder-like material because the peaks are quite sharp and tall. You see, the peaks are very tall. So this is not nanomaterial. It could not be a nanomaterial. But these are nanomaterial. The point is that for a single material, in here cadmium telluride, in both cases, here is a cadmium telluride and here is also cadmium telluride. But this is the macro powder, a large powder. This is the nanocrystal. It shows the reflection or diffraction of photons from a nanostructure. So basically, X-ray is a very easy and cheap method to get information about the crystal structure and also get some idea about the crystal size. The patterns on the bottom are from nanocrystals or cadmium telluride. But you should be careful when we are talking about the nanocrystal. We don't talk about the particle size. We are talking about the crystal itself because particles can contain many crystals. For example, you can have a powder which consists of 5 micrometer particles. So particles of 5 micrometer is quite large. It's very large. Okay, and you want the particle with the crystal size. So many nanocrystals can get together, stick together, agglomerate together, and form a large particle. Here, the large particle is 5 micrometer particle. So it's contained many nanocrystals, many small nanocrystals. Okay. So another question can be, actually, this is the one of the question the students asked in the previous semester, and it was a very good question. And they asked me if our nano material is nano sized in 1 or 2 direction, not in 3 dimension. So what will happen? What will look? What the how the XRD pattern will look like? I told them the planes of material which are parallel or in the direction of your uh, in the direction of your whisker or tube or nanotube will give you the large diffraction peak, and the planes which are not in parallel will give you the wide diffraction peak. So basically, you can recognize also nanowires or nanotubes by X-ray diffraction. And consider the X-ray XRD experiment is not expensive. It's around today is around the $4 or $5 for each sample in Iran. So you can simply understand if your material is nanocrystalline or not. Consider that the XRD does not talk about your crystal size, your particle size. It's only give you the crystal size. Okay? Let's have a break.